Hey everybody, welcome to today's lesson. I'm not sure if my webcam is actually working or not. It's not showing on my screen. I do apologize. But you know what? I'm not that important, so let's go ahead and get started on today's lesson about vapor pressure. I wanted to start today's lesson with just a quick video. Now, before I hit play on this video, I do want to make note that the temperature of our water, or the temperature of the sample of water that is in this video, is currently just under 24 degrees, so about 23.5 degrees Celsius. Now, based on what we've been discussing lately, I also want to note that we know that water should boil at 100 degrees Celsius. Now, what's particularly interesting about this sample of water is that it has been placed in what is called a vacuum chamber. In a vacuum chamber, what happens is a vacuum pump is turned on, and the air from inside of the vacuum chamber, this bell chamber, is completely removed. And you're going to notice that when this vacuum pump gets switched on, we are going to end up seeing the sample of water go ahead and undergo some changes. So I'm just waiting for the bell chamber to be turned on here, and it should be done in about the next 5 seconds or so. Okay. And what we're going to start to notice here, the chamber is being turned on. Okay, and the air is beginning to be removed from the interior of the chamber. Now notice, okay, you should start to see that there are some bubbles forming. I want you to notice before this gets too crazy, has our temperature changed? Okay, so it looks like our temperature is still at 23 or just about 24 degrees. And notice, what do we see is happening with the water here, right? We start to see the water boil at just 24 degrees Celsius. All right, so what I want to do is I want to use this video, okay, to just take a moment here and talk about, okay, what is called vapor pressure. So before we jump in and talk about the vapor pressure itself, let's just go ahead and make note of what we saw in that video. So I want to say that water temp, okay, was just under 24 degrees. Let's just call it 23.8 degrees Celsius, okay? Water should boil, and again, should boil at 100 degrees Celsius, okay? As the vacuum chamber was turned on, air was removed, and the water boiled at 23.8 degrees Celsius. And that's kind of crazy, and that should seem a little bit crazy to you because that is a very cold temperature for water to boil. And so what we're going to be talking about today is why did we see the water boil at such a low temperature when we know that water should boil at 100 degrees Celsius. Now, to jumpstart this conversation, I do want to talk just really quickly about evaporation and boiling. Okay, so evaporation and boiling, they sometimes get used interchangeably. Oftentimes when I ask my students about the phase change that happens from liquid to gas, I'll get half of the class saying evaporation and I'll get half of the class saying boiling. They are both a process in which liquid does form a gas, right? They are both vaporization processes. However, there are some slight differences between the two, okay? And so let's just go ahead and jot those down. So first, and this image actually does a great job of showing this. One of the major differences between these two is that evaporation only occurs at the surface of the liquid. Okay, so if, for example, I were to leave a large glass of water out overnight, you'll notice that maybe you'll have lost a little bit of water, but you're not going to lose extensive amounts of water because it's only occurring at the surface. And the surface area on that glass of water is actually very small. Okay, boiling, on the other hand, okay, occurs throughout the entirety of the liquid. Okay, and this, again, you can see that in the image. The evaporation is occurring only at the surface, and the boiling, you can see the bubbles coming throughout the entire sample. And the second major difference, and I'm only going to really go into these two, but the second major difference is really important. Okay, evaporation can occur at any temperature, right? So evaporation occurs at any temp. So, for example, like I just mentioned, if I were to sit and leave a glass of water out for a couple nights on my nightstand, okay, we might end up seeing that water decrease in value, even though, or even in the amount of it that we have, even though we aren't actually heating it to 100 degrees Celsius, okay? On the other hand, boiling is temperature dependent. Okay, so boiling is temperature dependent. Okay, it can only really happen at specific temperatures. Okay, and again, those are our two major differences between evaporation and boiling. So I do want you to kind of keep those in mind throughout this conversation and recognize that we're pretty much going to be focusing on just the boiling aspect of vaporization for today's lesson. All right, so let's jump into the main purpose of today's discussion, which is vapor pressure. So vapor pressure is one of those definitions for me in chemistry that was always really hard to understand, the textbooky definition of it. And so I'm not going to give you the textbooky definition. I'm going to try to define this in a way that will make it a little bit easier for you to understand. And so vapor pressure, okay, is going to be a measure of the tendency of a material to change into the gaseous or vapor state, hence why it's called vapor pressure. Okay, and so it's essentially a measure of, and like I always like to define it like this, so I'm going to add this at the bottom, but it's kind of, in my eyes, it's a measure of how much does a liquid or a solid, I guess, want to become a gas. Okay, so if, for example, you have a really high vapor pressure, then that means that you have a high tendency to become a gas. Okay, so the higher the vapor pressure, the more likely the substance is to become a gas. Now, something that I love, at least in terms of this course and the understanding of vapor pressure, is that you're actually provided an entire reference table dedicated specifically to vapor pressure. So if you were to flip to your reference table, this is going to be located at reference table H. And again, I urge you, if you do have yours handy, to make sure that you do pull it out and take a look at it. Don't always just focus on the ones that I have on these notes sheets, but this is reference table H, and it is called, I believe, the vapor pressure of 4 liquids, okay? And so something that I want to point out here, it's a measure of the vapor pressure versus the temperature. And so you'll notice that if we increase our temperature, and if we let's just focus on one line, right? Let's just say we're focusing on the line of water. If we increase temperature, what happens to the vapor pressure of water, right? So as we go from 0 degrees, where our vapor pressure is very low, to let's say 125 degrees, you'll notice our vapor pressure increases significantly. Now, this should really click and make a lot of sense in your mind. If I heat something up, it is more likely to change to the gaseous phase. So, something to make note of here, okay, vapor pressure increases with an increase in temperature, okay? And again, if you think about that definition of temperature, temperature is the movement of our particles, a measure of the average kinetic energy. And so if we are increasing the speed of those particles, then those particles are more likely to have enough speed to become the gaseous phase. Now what I want to do quickly is go ahead and compare the vapor pressure of two different liquids and kind of talk about why we see varying different vapor pressures, right? So if you look at the four liquids, and again, let's keep it consistent. Let's just say we're looking at the vapor pressure at 75 degrees. You'll notice that our lowest vapor pressure, the substance least likely to become a gas, is ethanoic acid. The substance with the greatest vapor pressure, or most likely to become a gas, is propanone. And the question is, why, even though we're at the same temperature, do we see such a variation in the vapor pressure between these two liquids? And it has to do with everything with structure, okay? So first, before I get into the structure though, I'm skipping ahead of myself. How does the vapor pressure of water compare to the vapor pressure of propanone at 65 degrees? So 65 degrees, okay? Water has a vapor pressure of about 22 kPa or kilopascals. That's going to be our measure of pressure, kilopascals, okay? And we're going to go all the way up to propanone, which has just, let's see, 110, 20, 30, maybe a 132 kPa, somewhere around there. So propanone has a greater vapor pressure than water. And so what does that mean? Again, think back to that definition. That means that propanone is more likely to be a gas than water at that given temperature. And so let's tie this back to the structures of our two molecules. Why is it that propanone is likely a gas and water likely isn't? Looking at the structure of propanone right here, okay, notice that our structure is symmetrical. And because our structure is symmetrical, that means it's considered nonpolar, okay? Versus our structure of water, which is asymmetrical, which means that it is polar. So in terms of what that molecular polarity means for us, we'd have to think back to our intermolecular forces of attraction. Which one of these two molecules experiences stronger intermolecular forces of attraction? Well, let's just quickly review, okay? What type of intermolecular force of attraction does propanone experience, okay? Because it is considered nonpolar, it's going to experience those London dispersion forces, okay? And because water is polar, we would probably say it experiences dipole-dipole forces. But you do need to ask yourself, does it fall under our special dipole-dipole force of hydrogen bonding? Because it contains those HO bonds, it does fall under that, and it experiences hydrogen bonding. So we know that hydrogen bonding is a much stronger intermolecular force of attraction compared to London dispersion forces. And so the reason that we experience this difference in vapor pressure And the significant difference in vapor pressure between these two is because water has stronger intermolecular forces of attraction. Therefore, it is less likely to be a gas. Okay? And so looking at our graph here, our vapor pressure for liquids, if we go from left to right, our intermolecular forces increase, our attractive forces increase. So ethanoic acid has our strongest intermolecular forces of attraction, and propanone has our weakest intermolecular forces of attraction. Okay? I can't believe I almost skipped over this entire thing. I think what happened here is I had a box that somehow got hidden. So I don't have anywhere specifically to write this, so I'm going to use my graph. Okay? So the question is, when does a substance boil? Okay? And we need to kind of think about here two separate forces. So in order for a substance to boil, our vapor particles, our gas particles, have to be able to escape our liquid. Okay, so there are two opposing forces here. We have our vapor pressures trying to push upward and escape the liquid phase. Okay, right? So if I wanted to, I don't know, I don't even have a good idea for what I want to say here. But if I wanted to, if I was a liquid and I wanted to become a gas, I would have to be able to escape the liquid phase. I have to be able to overcome those intermolecular forces and go out of my liquid phase. However, there's an opposing force of attraction that's coming down on me, okay? And that's called atmospheric pressure. And atmospheric pressure is all of the gas particles that already exist in the atmosphere pushing down onto the surface of that liquid, okay? And there may be days, and you may have experienced this, where you walk outside and the day feels really heavy to you. The air feels really heavy. And that's because the atmospheric pressure, depending on weather, and depending on a couple of other things, can change, okay? So we have our pressure pushing downward, and we have our gas particles trying to escape upward. And so I always kind of explain this to my students in class as like a kind of a funny story. This is really awful of me and my friends when we were younger. But my friend's younger sister had a toy box, and we always used to convince her to go into that toy box, okay? And then we would sit on the top of it, which is really, really mean, right? She's younger, she's weaker, she has no way to escape that. But if you can envision that situation, in order for those liquid particles to escape the gas phase, they have to be able to push up with enough force, aka the vapor pressure has to be great enough to overcome that atmospheric pressure, okay? So vapor pressure has to be equal to or greater than atmospheric pressure in order for the gas to escape, okay? So let's keep that, actually, let's jot that down. Okay, let's jot that down on this graph. So in order to boil, okay, gas or vapor pressure must be equal to or greater than atmospheric pressure. Okay, so when we are looking at this graph, this table H graph, you'll notice that on the y-axis we have vapor pressure listed. Okay, I want you to use that now as not only thinking of that as vapor pressure, but also atmospheric pressure. Because again, in order for something to boil, they are going to have to be the same value, atmospheric pressure. Okay, and so we have our vapor pressure, we have our atmospheric pressure. Now, just because I want to point out that standard pressure is a thing that exists, what is the normal boiling point of water? We mentioned this at the beginning of the video. What is the normal boiling point of water? Okay, water normally boils at 100 degrees Celsius. Okay, so this is our normal boiling point of water. And so the normal boiling point of water occurs when the atmospheric pressure is at what we call standard pressure. Okay, and so standard pressure is this 101.3 kPa. All right, I'm looking at the time on this video and I'm already at almost 20 minutes. So I'm gonna leave those last two questions at the bottom of this notes sheet for tomorrow in class, and we're gonna talk about those together. All right, everybody, have a great rest of your day, and I will see you guys tomorrow.